Welcome, good morning, everyone, and welcome to SAGE Live December 2023. My name is Ana Llubet, and I'm here from Los Alamos National Laboratory, talking to you from New Mexico. Before we start, let me briefly explain what SAGE Journey is all about and how SAGE Live, these events that we organize once a month, fits in that journey. SAGE Journey is a program whose mission is to inspire and encourage students to explore STEM careers for their future. And we hope that we show you all that with those talks. We do this by offering free summer camps that you have attended or you have volunteered, as well as paid internships, professional growth sessions, and many opportunities to connect with professionals who care about you and your future. We hope to be your cheer people and to help you find your way. SAGE Live is part of the SAGE Journey, and it's an online gathering of students who have attended the camps and are curious about the next steps in the SAGE Journey. So it is also a time to reconnect with the SAGE volunteers. I hope that many of you recognize some of the volunteers in your camps. We are here for you. It is held monthly via Zoom between the months of August and May, and the topics that we try to cover are relevant to your journey. Please propose topics. If it is something that you want to hear about, please let us know. With the topics that we tackle are career related, such as designing your life, resume workshop, how to prepare for an interview, or new and exciting topics such as quantum computing, AI, and machine learning, or astrophysics like today. So today we will talk about astrophysics, and we have a special master of ceremonies to lead this talk. His name is Alex Leader, and he will introduce himself and then the speaker. The floor is yours, Alex.
Hi, all. So my name is Alex Leader. I am also now joining you all from Los Alamos, New Mexico, where I just got hired as a research scientist here at the lab. But I've worked in physics research for many, many years, and I've worked on a huge number of experiments, including looking for dark matter deep underground, looking for the slightest hints of neutrinos coming out of nuclear reactors, to getting to spend a lovely couple of months during my thesis work in Paris, eating baguettes, and also, I guess, doing research, working on trying to measure some of the slowest nuclear decay processes known to man. And now I did my postdoc in the Bay Area, where I just came from. And in the Bay Area, I was also looking for a different kind of dark matter and trying to build some of the world's most sensitive electromagnetic antennas to try to find about dark matter. So if you're interested in that, I'm happy to answer any questions about this. It all falls under my purview and lots of experience. But my role today is to introduce our speaker and to run this, to help run this event. And I have to warn, or I have to say that I did my graduate school at MIT, so I may be throwing a little bit of shade at Caltech because, that's prescribed in the MIT charter. So just FYI. So, but without further ado, we have a speaker today from the West Coast School of Engineering, Caltech, and a Science and Engineering Institute that marshals some of the most innovative tools to address some of the most fundamental scientific questions. And they have a bunch of really awesome facilities on campus. I've been many times. It's a really, really great place. But throughout this talk, feel free to ask questions either in the chat, or you can send either one of us a private message if you prefer. And we'll be sure to address those questions at the end of the talk or during our Q&A session afterwards. So without further ado, I wish to present the speaker. Aisha is a Polish astrophysicist, specializing in the physics of galaxies and massive black holes, residing at galactic centers, a very, very active and a very fascinating field of research that, as a dark matter hunter, I like to follow quite a lot as well. In May 2023, she joined the High Energy Astrophysics group at Caltech, and to study the behavior of gases flowing around some of the most massive black holes in the local universe. And before that, she was at the University of Cambridge, earning her PhD, where she focused on understanding, again, black hole galaxy connections, and physical processes responsible for shutting down star formation in local galaxies. And outside of research, Aisha is passionate about science communication, as evidenced by her being here and her very professional speaker setup that you will be soon hearing. And you're always excited to hear about the cutting edge research to the broader public. So without further ado, I hand the floor over to our speaker.
Hi, Alex. Thank you so very much. What an incredible introduction. Not only am I humbled, I'm also deeply entertained. So let me try sharing my screen correctly. As we all know, it always works in principle, and in practice, it's different. So can I get some feedback on whether you're seeing the correct thing or not?
Yes, I can see your titles page.
Perfect. Fantastic. So hi, everyone. Again, as introduced, my name is Asia, which is actually short for Joanna in my mother tongue, Polish. And today I would like to talk to you a little bit about what I've been puzzled by for the past couple of years of research or so. And as Alex has correctly pointed out, I've recently joined the high energy astrophysics group at Caltech. And for me, this is the first professional research job after my PhD. So that's the moment when I start entertaining the idea of calling myself a professional researcher. Although depending on who you ask, some people call postdoctoral researchers postdoctoral students. I think that's exactly what my boss thinks. So I'm currently being mentored to become the better researcher that I am. But jokes aside, my focus of research is the study of supermassive black holes, a simulation of which I'm showing you on the left-hand side here. Now, to put it in a broader background, and I promise I'll get to the cool stuff in a second, I study the local universe. And what that means, I'm looking back in time no further than around 2 billion years. And within that look back time in the universe, I focus on galaxies and more importantly, supermassive black holes residing at their centers. So the way I envisaged this talk today is a play in 3 acts, if you will. I'd like to tell you a little bit about what galaxies are and how they come to be, or at least how we believe they come to be, what black holes are, or how we describe them, and how it is at all possible that objects so comparatively small can have a profound influence on the galaxies surrounding them. And as a final note, once we've already all lost our focus, because as we all know, focus span is limited for everyone, and the older you get, the worse it gets. So you guys are the nicest brains to accept all of that information. But once you're already quite tired, I'll tell you a little bit more about how my journey in astrophysics looked like, and hopefully convince you that there is no one way to do this. So as I've mentioned, we'll be talking about galaxies, and you may know them from looking up in the sky. You can do that definitely in New Mexico, where Los Alamos is. Simply look up in the sky and see this collection, the local overdensity of light in the sky, that by ancient Greeks has been compared to milk spilled across our celestial sphere, hence our own Milky Way. So that's what galaxies look
Did we lose Asha for
We lost
Yeah.
you, but I think she's back.
Have you
now.
lost me? Or am I
Yes.
back?
You're
Yeah,
back.
you're back.
What happened?
I don't know. We
You
lost your
froze
slides.
at,
Yeah.
Where did I
Latvia.
freeze? Did I freeze here or did I freeze earlier?
Earlier.
Oh no, that is very bad. Have I frozen here? Can I get some? Can I
It's
get
a
some
Milky
feedback,
in the
please?
Milky Way.
There.
Okay, so I froze on the Milky Way. It's not a bad place. Well, it's not a bad place to freeze, but jokes aside, you can see it again, right?
Yes. Well,
Perfect. I do apologize. Potentially, internet decided to cut off for a second right there. So as I was saying, hopefully, well, potentially into the void, which is quite appropriate when you talk about the universe, galaxies can also look like that when you're not looking at them from within, And I'm showing you Andromeda galaxy here. So if you ever had binoculars held to your eyes at some point, you might be able to see this image too. So what a galaxy is, and this will be our working definition for the rest of this talk, it's this collection, large collection of things that we can see, i.e. stars, gas, and dust, where dust is, imagine dust on your computer screen, but slightly bigger and maybe a little bit more chunky, and things that we cannot see, which is dark matter, Alex winking here at you, and of course, supermassive black holes. Now, Alex could probably tell you a lot more about what dark matter is, but for the purpose of this discussion, it is simply the overwhelming majority of matter in the universe, unfortunately, one that does not emit any radiation. And the reason why we know it exists is because all of those large accumulations of dark matter, for example, bend light that travels through us from distant galaxies, and we see the effect of all of that concentration of matter on the light signal observed on Earth. So we know what galaxies are composed of, but from where I sit, or from where my PhD sits, galaxies are also the end product of structure formation in the universe. And what I mean by this is that, well, I stopped here because I can't see anybody. And I'm just worried that there's nobody in there.
We are here.
I'm lost again.
We can hear you.
Good.
Okay, so I'm so sorry, because for a moment everything went dark.
We hear the Los Angeles turmoil.
Oh, do you? Oh, that's not great, is it? Shall I?
It's not that
good.
Yes, yes. Los Angeles is not the quietest city out there. But yeah, coming back to galaxies. From where research sits, really, galaxies are the end product of structure formation in the universe. And what I mean by this, if you were to take a full physics model of what you expect the universe to be, and start with a good set of initial conditions, i.e. a starting point for your universe. And here I'm showing you the record of first ever radiation emitted in the history of the universe, called the cosmic microwave background. The blue and orange things, the blue and orange splotches indicate the differences in density or temperature in the early universe. So if you were to take this as an initial condition, plug it into a supercomputer and run it for long enough time, you would expect to see structure formation in the universe. And in each of those individual dots right here, you would expect for galaxies to lie. Now here, I'm showing you a dark matter only simulation, in which case we're only simulating this invisible component of galaxies. We're not talking about all the matter that we're composed of, the gas, the stars. We're only looking at dark matter. And what you see as a function of time, at early times, the universe is pretty homogeneous, like the cosmic microwave background looked to the unaided eye. Then as time progresses, these local overdensities become denser, hence creating this elaborate structure that we call the cosmic web. Now, within all of those densities, overdensities that I alluded to, we expect regular matter to aggregate and hence form galaxies. And that's what I mean by galaxies being the end point of structure formation in the universe. Gas and things that emit light follows the distribution of dark matter, which creates those deep gravitational potential wells, and within those wells we expect galaxies to form. And in fact, you can take one of those simulations and ask, well, what do you expect the universe to look like? Or let me rephrase that question, where do you expect galaxies to lie in the observable universe, assuming that those simulations are true? And that is what you can see in these blue dots here. You're effectively seeing this splotchy collection of little dots that simulations predict. And then you compare it with where the galaxies are measured to lie in the universe. That's all the yellow bits here on the other half of the diagram. And even by eye, you can tell that the correspondence between these two slices is absolutely remarkable. So at this point, you might think, well, universe solved, right? We know how dark matter behaves, and we hopefully have a good understanding of our cosmological model of the universe. That's a totally separate story. And we have just solved everything that has to pertain to galaxies. Now, I would be out of job if that was really the case, of course. But luckily for me, that's not the end of the story. Now, if you were to look a little bit more closely at the pictures I've shown you before that we derived from cosmological simulations, one of which I'm showing you here in the background, mostly for visual purposes because I think it's absolutely great, but also because it illustrates the point quite well. You can ask how many massive dark matter collections you require, that's the y-axis, as a function of how massive they are. Effectively, you're counting how many things of a given mass you have. And that is what simulations predict, this dashed line. Now, all well and good. Now you take that distribution of galaxies that we've seen matched perfectly the simulations and ask, well, what happens to galaxy sizes or luminosities because light translates to mass? And suddenly you realize that, hold on a minute, the picture is not quite complete because we're missing things that are low mass and we're missing things that are high mass. So the universe seems to be underproducing galaxies that are both very massive or very bright and very low mass, or very low brightness, very low luminosity, sorry, I should say. So that's great, because that means there must be some physics that we need to account for in order to translate our dark matter only universe into galaxies. So you should simply understand that it's not only gravity that governs the evolutions of galaxies in the universe. There must be some more profound visible matter interactions that we need to deal with, and that brings me really to where the starting point for my research was during the PhD. So if you were to look at the night sky, and if you had good enough eyes, in that case, the eyes of Hubble Space Telescope, and if you were to stare at that night sky for long enough, the whole image I'm showing you in the slide is this tiny square called the Hubble Ultra Deep Field. And I call it tiny because this slide helpfully compares it to the size of the moon and other planets as visible from Earth. So it's an absolutely tiny patch of sky. Now, within that patch of sky, if you were to mask everything that is obviously a star, i.e. a star within the Milky Way, everything else, every single speck of dust, and there are thousands of those in this image, is an individual galaxy. So not only are there many of those, but also even by eye, you can tell they are not all equal. You see some things that look blue, some things that look red, and some things which for historical reasons we call green. They're not exactly green to an unaided eye, but let's live with that definition for a moment. Now, this visible dichotomy that we just saw by eye is a visual consequence of a more underlying fundamental bimodality in galaxy types. You've got the blue galaxies that are actively star forming and the red quiescent galaxies that look entirely different. So on the left-hand side, you've got things that you expect Milky Way to be with, full of young stars, a lot of structure, spiral arms along which you see a lot of star formation, if you will, a picture-perfect galaxy that you think of when Googling a Hubble image. Now, on the other side of the galactic scale, the red quiescent galaxies are completely different. They have smooth light distributions, have little to no new stars born, and are dominated by old stellar light. Now, when astronomers, much like myself, observe galaxy properties across cosmic time, and because of finite speed of light, the further you look back in time, the further in distance, the further in distance you look, the further back in time you look. So if we were to look at those galaxies as a function of cosmic time, we see that galaxy properties or galaxy groups shift from blue dominated to red dominated, and hence these two are interpreted as an evolutionary sequence in which blue star forming galaxies transition to become red in a process that we call galaxy quenching, by analogy of quenching by fire. So that brings me to the first takeaway of our talk today. And yes, I had ramen yesterday, so takeaway box for ramen it is. That galaxies in the universe come in two broad flavors, and we expect the blue star forming galaxies to evolve to become red and quiescent, and the main difference between them is how much stars they're forming. Great. So you might wonder, well, how does one exactly go about measuring this or studying this? And for people like myself, you cannot really do it with your own eyes. So on the one hand, we can use cosmological simulations, i.e. the simulations of a universe in a box where we put all the visible matter, dark matter, black holes, all the physics that we know in a single box and let it run to simulate the universe. So examples of these I'm showing you on the slide. And then you want to verify those cosmological simulations, which constitute your theoretical grounds, and go ahead and measure all of the observable universe. And when I say measure, I mean taking observations of millions of galaxies. And in fact, that's exactly the data set I used, taken with a telescope in New Mexico, called the Sloan Digital Sky Survey, where you simply look at large statistical samples of 1 million of galaxies. And that means that there is no way that a single PhD lifetime goes ahead, sits at a telescope and observes things all by themselves. In fact, it's all currently automated. So a day in the life of a postdoc in astrophysics or a PhD in astrophysics is really sitting in front of a computer. And I do apologize for this silly image, but when I looked through all of my photos, I realized I don't have pictures of me working at my desk. So the only picture I had was Halloween. So there you go. This was Halloween before leaving Cambridge. You can tell greenery outside, and I'm obviously Maleficent. Caption this image however you like, but yes, you can still do meaningful science and look the way you do in that silly image. So in practice, as an astrophysicist, you simply do a lot of programming, and while sitting at your desk, you also do a fair share of pen and paper calculations and sanity checks. Most importantly, for anyone who's starting in the field, you read plenty of scientific literature to make sure you understand what you're getting yourself into. Of course, once you have an idea, you also write proposals for observing the universe, because telescopes usually allow for submitting observation ideas that can then get selected by a committee, by a jury, and some science gets to be performed. You also share your results at meetings and conferences. Of course, write and publish your results in scientific journals. And something I most recently had the benefit of enjoying, you get to mentor students and teach them about your field of expertise. So in practice, the going to conferences thing is absolutely fantastic. Not only does it allow you to meet new fantastic people, but also you get to see places that you most likely wouldn't have seen otherwise. Here I am at the Great Wall of China. I'm very grateful for a conference in Beijing on galaxy evolution. Going to conferences also allows you to reconnect with people whom you haven't seen in a long while, either from your previous research projects or simply university and school. And as you can tell, for those of you with a keen eye, I seem to only have one t-shirt in my wardrobe because all of those pictures seem to have this particular sleeveless, sorry, not even t-shirt, sleeveless shirt, but that's beside the point. Also being an astrophysicist, yes, you don't you don't exactly need to be doing only science. You still have time for your hobbies, for sailing on ice, for fostering animals, or simply doing knitting. So being in the office is one thing, but more importantly, your head has to have balance in order to think creatively about the problems you're trying to solve. Sometimes you just need to put on a knitted hat. So with that interlude, hopefully, I can set the stage for what black holes are. And that brings me smoothly into the second part of our 3-act journey. So I promise that's the only equation I'm going to put on the slide. I call it the quick relativity recap, but what it really is an introduction into the idea that the distribution of matter in the universe simply curves the space-time, i.e. the 3 spatial dimensions and 1 temporal one we see in the universe. And what it translates to, if you were to think about the universe as a 2-dimensional membrane, if you have no mass, it is simply a flat sheet of paper. Things that carry some mass, like our own sun, tend to bend it. Now, black holes within that simple 2-dimensional analogy would be a bend in your membrane that extends infinitely downward. So a working definition of a black hole, and there are so many ways you could talk about black holes at a popular science level. So hopefully we can all agree for the purpose of this talk that black holes are objects so massive and compact that not even light cannot expect their gravitational potential wells. And to give you an idea of how compact is enough, well, I promise one equation, sorry, that's the second one. But it really doesn't matter. But if you use this relationship to tell you how large black holes can be, that's radius r with respect to their mass. A thing of the mass of the sun would squeeze into a ball of 3 kilometers in its radius. For a thing as large as our own moon, it would be the size smaller than, I guess, a single hair strand. If I don't know how large hair strands are, but I think that's a good analogy here. So black holes that I often think of, or majority of astrophysicists think of, come in 2 flavors. The solar mass kind, i.e. the end product of evolution of stars. These are black holes born in stellar explosions, and we expect them to be as massive as a couple of our sun's worth in a single black hole. They are scattered across galaxies, and within our own Milky Way. I've put a lot of zeros down there. I should probably read it real quick. And I think this is 10 to the 9 of those in the Milky Way expected to be. But please don't quote me on that. These these estimates vary strongly depending on your stellar population models. Now, the ones I feel most comfortable in are the supermassive kind. And for those of you who have watched Interstellar, you will recognize Gargantua. I absolutely love this image. Enjoyed Interstellar as a movie. Happy to talk about it if you're interested. But what is more important is that the supermassive kind of black hole is truly extraordinary. We don't know how they came to be. We don't know if they're the end product of stellar evolution, maybe at some early time in the universe. But what we do know is that each of those beasts, and we believe one of each sits in every galaxy, hold a mass of around 1 million solar masses and above. Now, of course, it's that's just our estimate of one per galaxy. Chances are there might be more hidden to our eyes, but that's not the subject of our chat today. Now that we know what, yes,
Asha, I think we lost you a little bit again.
How come?
And you're kind of frozen. I don't know if maybe you did one of those things, but I can see something green. I don't know if it's in.
How about
we can hear you well, but
you can hear me well?
Now we can. You were breaking. Now we can see you perfect. Yes.
Okay.
Great.
So you lost my face, but you didn't lose my audio?
Yes, exactly. I mean, you were there, but you were frozen. But now we can see you and hear you perfectly well. But we never stop
hearing
to
me.
you. So, yeah,
That's the most important bit. You don't need to see my face.
sorry
Okay.
sorry to interrupt.
Except when you are dressed up like Maleficent.
Oh yes.
That's okay. That's not today. But in all seriousness, if that is causing trouble, just let me know. I'll turn my video off and get back for the Q&A session. So I've introduced you to the idea of black holes, and it all sounds well and good, but do they really exist? I mean, hold on a minute, Asha. That sounds a little bit too wacky to be true. And I would argue we have 3 key pieces of evidence that they actually are real. And yes, is there a question? No? Okay. And one of those key pieces of evidence comes from gravitational wave measurements. In fact, arguably, if you translate the frequencies right, you can hear black holes collide, and I sure hope you guys will be able to hear it. So let's try it. Did that work? Did anyone hear the black holes collide?
I fear
No.
I did.
You did. Yay! Fantastic. So in case you didn't, don't worry. LIGO, the LIGO webpage has a whole range of recorded black hole collisions that you are more welcome to listen to. They're called chirps because of the particular shape of the signature they make.
Asha,
So-
can you do it again? We
Yes,
have
of
a
course.
request in the chat, so we can be
Absolutely.
very quiet. Let's see if we can
Oh,
do it.
very quiet. Hold on a minute. What if we try this? Was that any better?
I heard it, but it was also still very quiet.
Yeah.
Ah, mamma mia. How do I? It worked so well when we tested it right before the
You worked
meeting.
very well, like the room, like oh my god.
Oh, okay. I think I know what happened. Can we try again?
Yes, yes, yes.
Yep.
Yes, fantastic. So I think when I got disconnected for the first time, everything went away. But now I fixed it, so you could hear the black holes collide. And definitely go ahead and check them out on the LIGO interferometer website, because they have plenty more to see. So we can hear black holes. We can also take the picture of shadow they cast against matter that flows around them. So remember that simulation I showed you a while back in my opening slide? Well, this simulation is no longer just theory. It actually became reality thanks to the Event Horizon Telescope team, which combined multiple radio dishes across the entire Earth, turning our planet effectively into a single radio dish, allowing us to look with an Earth-sized telescope as close to the event horizon of supermassive black holes like our own Milky Way supermassive black hole, showing the space donut. And if you want to learn more about supermassive black holes as seen by Event Horizon Telescope, definitely visit their webpage. They have plenty of resources that are written in a very accessible, fun language. So the third piece of evidence, and one that actually won a Nobel Prize in astrophysics recently, back in 2020, is the observation that supermassive black holes directly influence the motion of stars around them. So if you look at the galactic center, our own Milky Way galactic center, and look at the motions of stars, these are these blurry blobs that keep on moving, you can clearly track their positions as a function of time and reverse engineer the amount of mass you expect within a very small region of space. And that is exactly what has been measured independently by two teams across the globe, led by Reinhard Genzel in Germany, Andrea Ghez, actually here at UCLA, winning Nobel Prize in 2020. And of course, the theoretical description of black holes is attributed, well, won Roger Penrose the Nobel Prize, and it was shared 50-50 between experiment and theory. So the reason why black holes allow us to study them is not because they make sounds when they collide or we need those expensive Earth-sized telescopes and these expensive measurements of galactic centers. In fact, black holes, and this will sound counterintuitive, are the most luminous objects in the universe. In fact, the first ever confirmed extragalactic object turned out to be a supermassive black hole known as a quasar. Oh, first time hearing a black hole, Anna. Ah, so glad. So quasars are simply supermassive black holes surrounded by disks of matter, and they are many more times more luminous than our own sun. They are extremely variable. They hold black holes with masses of around a million, this particular one, 1 billion masses of our own sun. And these are some of the most distant objects we see in the universe. So the question would be, what makes them shine so bright, right? Black holes don't emit light. That's the whole point. They are massive and compact enough so that even light cannot escape their gravitational potential wells. Well, they are powered by accretion, the most efficient engine known in the universe. So what I mean by this, if you have a black hole that's surrounded by clouds of gas, and these clouds of gas happen to be in motion, they will follow the, for the lack of a better word, attraction of the supermassive black hole, and because those clouds are in motion and there is angular momentum in the system, it gets to be conserved. So this gas settles into an accretion disk. Now, as matter flows through the accretion disk, losing its angular momentum through interactions, matter-matter interactions, it also gets to lose its gravitational potential energy and heat up and emit a lot of radiation in consequence. Now, how much radiation can be emitted in that process is absolutely astounding, because according to theoretical models that we still currently use, although 50 years old, they are still quite actively used in the field. We think that roughly 40% of, as much as 40% of the rest mass energy of matter that flows through the disk gets to be emitted in radiation. Now, compared to nuclear fusion, and I'm happy to be corrected here, this is an order of magnitude more than the process that powers light that shines from stars. Now, all of this radiation that gets emitted from the accretion disk has potential of dealing a lot of damage to the surrounding galaxy. Not only can all of this powerful light heat up the gas, but also it can drive powerful outflows that I'm trying to indicate in these funny PowerPoint green graphics. Now, black holes themselves are also non-stationary. They in fact rotate. And if you add magnetic fields into the picture, which, by the way, any astrophysicist hates when you think about, this is one of the favorite questions everyone asks in talks. You present your model, you discuss your conclusions, and then someone raises their hand and goes, but what about magnetic fields? Where in the case of black holes, they get twisted by the rotating supermassive black hole, and drain material from the disk, driving it out in these powerful jets. Now, these jets themselves do not only locally interact with the matter surrounding the black hole, but they can also deposit energy at faraway distances. Now, what does it look like in practice? Here I'm showing you a visualization of what a black hole surrounded by an accretion disk with a jet can look like. And things to note here is that this object is very small, point-like, and shines very, very bright. And in fact, some of the biggest studies we perform in supermassive black holes have to do with their emission in the X-ray wavelengths. So this is some of the highest energy radiation we observe in the universe. It's, of course, you wouldn't be able to see it with an unaided eye, but with space telescopes like NuSTAR, presented here on the slide, you can measure all of this powerful radiation and say something about how black holes grow. So that's takeaway number 2. Supermassive black holes are some of the most luminous objects in the universe, and with all of that matter surrounding them and radiation released from around the black holes, they have a very strong potential for dealing damage to their surrounding galaxies. And what they look like not in X-ray, but rather if we were to have our space telescope eyes within the optical regime, that's what these bright black holes would look like. So on many an occasion, you can very barely see the galaxy around it, and this point-like, very bright source right at the center, which is nothing else than the black hole in its accretion disk. Similarly here, although with that galaxy actively forming stars a little bit more, it gets to be brighter and not outshone entirely. Now, if you combine distant quasars with the presence of dark matter in front of it, you can even see multiple images of the same supermassive black hole with an accretion disk due to gravitational lensing, and this is definitely area where Alex has plenty to talk about. So I told you about those jets, but I haven't shown them to you yet, because when you look at a black hole face on, this jet would be facing right in your eyes, so you wouldn't be able to see it. Now, if you look at a galaxy edge on, like on the left-hand side here, the galaxy is enshrouded in this streak of gas and dust, and the jets launched by a black hole reach towards very high distances around the galaxy into what we call the circumgalactic medium, or effectively gas surrounding galaxies. So that's just one example, and I'm sure you have seen that image before. Now on the right hand side, that's another very famous object called M87. In fact, we have a supermassive black hole shadow picture from M87 too by the Event Horizon Telescope, and that would be just tiny dot here in the center. But more importantly, I would like you to notice those orangey reddish large structures that are telltale signs of where jets used to be and interacted with matter. So as I've told you before, these jets can reach very high distances around their host galaxies, and that's where they get to deposit all of that energy pent up from accretion. And by doing so, those tiny black holes, tiny in comparison to their massive galaxies, get to influence the entire journey galaxies take through the universe. So that's takeaway number 3. Supermassive black holes are tiny yet mighty. And in practice, what it looks like if you were to look at the whole selection of galaxies across the sky, supermassive black holes, I mentioned them being tiny, but I didn't quantify how tiny I mean. These are objects of masses around 1,000 times less or more than their host galaxies. So this comparatively tiny speck of dust is able to launch enough energy into space surrounding galaxies that not only does it disrupt the star formation and galaxies themselves, but more importantly, it keeps the gas surrounding galaxies hot, preventing it from falling onto galaxies again and forming new stars. And some of the most spectacular examples of jets I was talking about are visible in Hercules A system, observed with in radio wavelengths. When you see those very pencil thin jets that reach towards very high distances, this is just a galaxy, right? And everything else is a jet. So you can see that these supermassive black hole jets successfully launched to very high distances have a profound influence on how galaxies evolve. So that will be the end of my science journey, and I'm hoping to leave you with the 3 takeaways I mentioned. Well, it's not the science journey, the end of my science chapter. And I'm hoping to leave you with 3 key takeaways. I want you to remember that over lifetime, galaxies transition from their blue star forming to the red quiescent state. And this is an evolutionary scenario for which we seem to be missing key pieces of physics that we have yet to understand completely. Now, some of the relief to this misunderstanding may come from detailed studies of supermassive black holes, which are some of the most luminous objects in the universe, and the reason why they emit so much radiation is because they're surrounded by extended disks of matter that gets hot and shines. Now, finally, those comparatively tiny black hole can deal a fair share of damage to their host galaxies. And I would argue that the primary reason why they kill star formation is by launching these powerful jets. I hopefully convinced you are quite a monstrous force in the observable universe. Now, as a final note, I wanted to show you what a journey through astrophysics can look like. So I'm myself Polish. I was in fact born in Warsaw, and a long while back, you can't really read Polish, but listopat is November. So around November 2008, I came across this cover of the Polish version of Scientific American, and I must admit I did not understand a thing from reading that article back then, but I definitely enjoyed the graphics and got fascinated by the universe that I could experience with my own eyes, or at least through a newspaper, but couldn't quite understand. So in order to understand it better, I joined the Polish Association of Amateur Astronomers. As you can tell, there is a slight discrepancy. There is a slight discrepancy between the average age of me and the rest of the Polish Association of Amateur Astronomers. But don't worry, it gets better with time. More women joined, and we're having a lovely time. Now, what this Polish Association of Amateur Astronomers helped me do, they opened my eyes to the cosmos through actual telescopes, because obviously I didn't have one, but through a telescope like the one presented on the slide, I got to see Saturn for the very first time. And I see there are questions in the chat. So let me real quick read them, because
we can ask them at the end, Asha.
Oh, we can ask them at the end?
Yeah,
okay.
yeah.
Okay, cool. Happy to answer.
We'll collect them and then give you them all to you in a one big package.
Fantastic. Thank you very much.
Oh no, your video froze again. I think
Oh no!
the expression.
But she looked like an angel with the thing.
Life is not okay. Life is not okay with these impressions. I turned them off, I swear. Okay. Can you hear me and see me now?
Yes. Everything's fine.
Oh no. Okay, cool. So so genuinely what I want to express here is that my road into physics did not come from necessarily textbooks. It came from looking at the sky and wondering what those glistening things in the distance were. And thanks to people like all of my friends in the Polish Association of Amateur Astronomers, PTMA for short, I got to experience it firsthand and even see Saturn. And yes, I did cry. It was so beautiful. So having developed these interests a little bit in Poland, I then was frankly lucky enough to pursue an undergraduate degree all the way in the UK. And I say lucky enough because I actually wanted to be an artist. There was one subject I struggled with, and that was physics. And my friends in high school, they were aiming for these incredible universities all across the world, and I thought, okay, they're applying, I might apply too. And luck had it that it panned out the right way. And so I spent 4 years doing a course called Natural Sciences, which meant that I was not a physicist to start with. I actually had to dabble in geology, physics, mathematics, and materials science, which then narrowed down to physics and mathematics, physics only, and finally, astrophysics in my 4th year. Now, that was not really, university itself was not really the defining moment for understanding that I would like to be a researcher. The turning point came with a breakthrough research project I had a chance to do at Perimeter Institute in Waterloo, Canada, where an incredible mentor who's now at the Los Alamos National Lab, Jonah Miller, offered a project to develop numerical methods, an alternative class of numerical methods. And the project was fascinating enough and went well enough that Jonah then invited me to come to the Los Alamos National Lab to follow up on this. And that's how I got to meet Anna, get engaged in the summer physics camp for for young women in northern New Mexico. And that's how effectively I ended up here talking to you today. So one of the most important things I'd like to stress here, and I don't mean to wax lyrical about Jonah, but the turning point for understanding that research can be done came with a truly supportive supervisor who trusted my ability to perform research, who trusted my creativity, and most importantly, gave me a full ownership of the project. So not only did I get to learn, but also I got to explore science at my own terms with the full trust of someone that I'm capable enough to do this. And from that moment on, I actually got to do a PhD. And this is our whole PhD family. For those of you with a keen eye, you can tell this is not a real, entirely real photo. There are some people who are photoshopped, some better than others. The reason being, I'm not that good at Photoshop, or let me rephrase that, I'm just not good at Photoshop. But what you can tell in this image is that we're quite a happy, diverse group of people. And among these, I was on a good streak with supportive supervisors, both of whom taught me incredibly well during my PhD. And thanks to them, I'm here right now in California speaking to you. It wouldn't happen without them. Now, what you also can see in this image is that our research group was fairly welcoming. I wasn't the only female student in the group. In fact, there were so many other female students and female postdocs. I had people to look up to. And that is so incredibly important, and part of the reason why the SAGE camp is so valuable. You get to see other people just like you at a different career stage, and you say, or think to yourself, well, actually, I can probably do that. And that's true, because you can. And sometimes the world doesn't go the way you plan. So in my case, moving countries didn't quite work out as I wanted it to be. I graduated back in October. I was supposed to, October 2022, was supposed to start my postdoc at Caltech around that time. But, you know, immigration got in the way. So I only reached California in May 2023 with my belongings in a rather dire state. Luckily, some of the most important things that I chose to ship, like my GR textbook by Robert Wald, remained untouched by this terrible experience, so I count it as a success. And that's what brought me here, to Caltech, to this incredible team of absolutely inspiring, supportive people who collectively, as a team, get to do great science. Now, that's just my journey. And if there's anything I could leave you with from my personal standpoint that isn't science, not the ramen takeaways, but something personal, I'd like to ask you to just stay curious. Because at the end of the day, that curiosity is what drives some of the most important and consequential decisions in your life. And within staying curious, just make sure to just be you. The brave, colorful, and absolutely unique, fantastic you. So on that note, you probably know how to reach me. My email is on the opening slide. Feel free to contact me anytime. I'm always happy to have a chat. Thank you very much.
Thank you. That was an amazing talk, and I learned a bunch. I mean, I've been in this field for many years, and there's always something new to learn. So as we mentioned in the talk, if you have questions, please feel free to put them in the chat. I'll read through them and let our esteemed speaker and colleague answer them and give her insights. So, without any further ado, I'm going to go to the first question that was asked by Ariana Reyes Noel, namely, in the simulations of the stars going around a black hole and changing direction, would a star that enters directly in the black hole simply not come out?
Oh, that's an excellent question. Thank
That's
you.
actually a question that my daughter asked, my junior, Dalia. Say hi.
Hi.
That's an excellent question, Dalia, right?
Yeah.
Dalia.
Yes. That's an excellent question, and the answer is yes. In fact, it very rarely happens that that stars would be on a direct collision path to a black hole and be swallowed completely. But what happens and creates some of the most exciting short-lived observations in the universe, stars get very close to black holes and they get pulled apart, literally stripped into a cloud of gas that temporarily becomes a black hole accretion disk, and we call it the tidal disruption event. And this is one of the most exciting areas of observation right now. And here at Caltech, we've got a whole team championing search for these exotic events in the local universe.
Great.
Excellent question.
Thank you.
Moving on to the next question from the chat, we have another question from Jasmine Sanhu asking, do black holes and supermassive black holes have different lifespans, or is it simply so long that any difference is negligible? Are growth rates of black holes and supermassive black holes different?
Click the wrong button, sorry. So first of all, two great questions. And the first one, to answer the first one, in the cosmic scale of things, the difference in supermassive black hole lifetimes are probably negligible. Negligible in a sense that we believe they formed rather early on, and whatever measurement we even dare to make right now that would infer this age will probably have uncertainties that are much longer than even the lifetime of those black holes. So for the purpose of measuring it, it really doesn't matter. But it is an exciting area of research now that we have James Webb Space Telescope, and we're trying to look at some of the most distant massive black holes in the universe, and we're arguing how old they were, how early they're formed, and how quickly they grew their mass, because some of them seem to be violating models that we've been using for a while now. But that's obviously a separate discussion, and I would be excited to talk about it in maybe 5 years' time once James Webb collects enough sample sizes to talk about it with statistical certainty. Now, another question was the difference in the growth rate between supermassive and stellar mass black holes, and that's an excellent question. So, in fact, supermassive black holes tend to be surrounded by plenty of gas available for accretion, and they tend to grow much faster than their stellar mass equivalent, simply because black holes of the size of, say, a couple solar masses, they are unlikely to be feeding on something unless they are in a binary system in which they're slowly gobbling up their companion star. So at most, what they can do, they can eat up a couple stars worth of mass over their lifetime, while supermassive black holes will get to grow much faster than that. And how fast exactly? Well, I defer that question to full physics modeling of accretion in these extreme states, but that is faster than, it can be much faster than accretion rates of stellar mass black holes, depending on which model you focus on.
Great. Thank you. Next question comes from Edda Grondal. Namely, thank you so much for this. I learned so much. Then, though, through what processes do blue galaxies become red quiescent galaxies, or is it simply through time?
Great question. So some of those galaxies will become redder simply through time because they will eat up the gas that is available to them, and there will be no more fuel for future star formation. And if they happen to live in dense enough environments, they may be stripped of gas additionally. But more importantly, just secular processes, i.e., just through time, is not enough to prevent galaxies from forming new stars. And that's exactly where black holes come into play. And more importantly, the jets they launch at those large distances, because if you were to ask me what is the most important process for preventing star formation in galaxies, that would be the launching of these jets, because what they do at these large distances away from galaxies, they will keep the gas from accreting onto the galaxy from within the cosmic web, and hence fueling future star formation. So secularly, a galaxy may just use up its fuel, but something has to prevent it from gaining new fuel from the universe, and that something is exactly black holes.
As a follow-up, somebody in the chat, Andrea, asked, is that star recycling?
Ooh, star recycling. That's an excellent question. I think star recycling. For the purpose of new star formation, we only focus on gas, because stars themselves do not get recycled once they're born. They simply live out their lifetimes. But an interesting point associated with recycling is the idea of a galactic fountain. So sometimes you get gas blown out of the galaxy, for example, by supernova explosions. And if those explosions are not powerful enough and galaxies are massive enough, all of that gas returns to those galaxies through gas recycling called the galactic fountain. And the reason why we call it a fountain is I'm trying to draw it with my hands. Simply you eject the gas, and then it comes back simply pulled back by the gravitational potential well. So stars do not get recycled per se, but the gas that new stars can be made of, yes, it can. Yes, it does. Yeah.
Great. So again, don't forget, if you have questions, don't forget to put them in the chat, and we'll happily answer. And then a question and your book.
What?
There are requests for links to your book.
I suspect it's your thesis, Asha.
Oh, my thesis. Actually, we're laughing, but the advice I got for my thesis was to write the introduction chapter, or at least the first part of the introduction, at a level that my parents would understand. And trust me, anyone in this call, surely, if my parents could handle it, everyone could handle this. So, so I can probably find a link to my thesis if you're interested in reading the introduction. I flesh out this idea somewhat well. Now, if you're, oh wait, I have a book? No, I don't have a book. I don't have a. Oh wait. You mean recently? I was part of an initiative by the Canadian Life Science Institute. Oh wow, I got it wrong. Life Beyond Us. It was a collection of short stories together with supporting science articles that talked about alternative ideas for life outside of Earth. And these short stories are novels, sci-fi novels, and I had the pleasure of working with Peter Watts, advising him on his exciting novel, and I got to be one of the characters. One of the characters is named after me, so that's very exciting. But jokes aside, Life Beyond Us is a great collection of interesting scientific ideas and, most importantly, exciting sci-fi stories. So if anyone is interested, definitely check it out. It's a great effort put together by some of the best modern writers.
And following up with a request for a link, we'll see if we can put that in the either in the chat or in some of the social media materials afterwards.
That's probably easier.
A question from the chat: are you still doing art?
Great question. I actually do. I do, and it will always stay with me for a lifetime, because that's the way for my brain to unwind. Sometimes when I meet difficult problems, conceptual problems, people take showers, take long walks. All of these things work, but for me, focusing on the motoric action is really quite soothing. And And to show you an example of what art I actually make, sometimes it's inspired by the universe. So the background of my slides is a pair of supermassive black holes surrounded by misaligned accretion disks that follow cosmic dance for millions of years on end, and will finally end up coming close enough together for gravitational wave radiation to carry away their angular momentum and merge. And we'll get to see those objects or hear those objects with the LISA mission, which will be, think of it as LIGO but launched in space. So art like this is still very much on my daily agenda.
Great. Then let's see, we have one more question from the chat, namely from Edda Grondal again. How are quasar ghosts formed?
How are quasar
Ghosts formed.
Oh, ghosts. Oh, I meant quasar hosts, maybe. So, well, first of all, how do quasars come to be? It's actually it's a non-trivial question, right? Because I told you these are supermassive black holes surrounded by disks of matter, but how does is this matter always present, and how does it even come close to a black hole? We believe some of the most spectacular events that cause quasars to shine follow from collisions of galaxies. So as galaxies collide, not only do they get mangled up, but also all of that mangling and violent relaxation of the system drives plenty of gas into the center where we expect supermassive black holes to be. So we believe some of the most powerful quasars that we find in the universe, they tend to be fueled by gas, which might be driven by collisions of galaxies, and hence this rapid throw of mass onto black holes. So that's hopefully that answers the question.
Great. Now some questions from me now.
Oh,
now you get to hear what the dark matter physicist thinks. Question. So you mentioned that there's a lot of new data coming in, James Webb, Sloan Digital Sky Survey, things like that. Is there any particular data set that you are excited for and that you think would be particularly illuminating for your work and could single-handedly blow the paradigm of structure formation wide open?
Oh, great question. So I don't think there is a single data set coming, because there will be a concert of multiple data sets coming up together. And we're talking about large sky surveys conducted by Euclid, the Roman telescope. There are in conjunction with surveys like DESI and all the other supporting missions. So for these names mean nothing when just thrown out in the air, but what they actually are observations of the same objects in the universe at different wavelengths, which allows you to understand galaxies completely, not only a snippet in, say, the visible part of the spectrum, but rather the whole of light information that you can get. And I am excited about those future synergies simply because in order to understand galaxies, those complex collections of stars, gas, dust, dark matter, and black holes, you really need that multi-wavelength observation, because not only does it allow you to reconstruct the current state of what galaxies are, but also play the game of what they were as a function of time. Now that, combined with where the galaxies are at present day, allows you to reconstruct the history of structure formation. I think the only way through to understanding galaxies is exactly through those multi-wavelength large statistical studies.
I think we have a hand raised from Anna.
Yeah. So how many of you have watched the movie Oppenheimer?
Several times.
Yeah, I see at least so one of the things that I had read about is how it's a question that I'm often asked: how do we decide to look for things, right? How do we decide to build a big accelerator? How do we decide to build a very large array? And for those of us, there's often a seed, someone who wrote a paper, talked about something. And in the case of J. Robert Oppenheimer, who was the first Los Alamos National Laboratory director, I just found a date. It says on September 1st, 1939, the same day that Germany attacked Poland and started World War II, the paper from J. Robert Oppenheimer, in which with his student Snyder, started to identify some singularities in equations, and they figured out that this singularity in this equation should have these properties. They didn't call it a black hole, but that's how the seed is planted. And of course, Oppenheimer got very busy for a variety of reasons throughout, and never came back to it. So, and he passed away in the 60s, and we are often asked, as you know, this year with the movie and so on, it was a big deal, and with the change of the clearance refusal, it was a big deal. But why did Oppenheimer never won a Nobel Prize for it? And we often answer, well, you cannot give a Nobel Prize to someone who passed away, right? So he came up with this idea. The idea remained latent until we had the technology to observe it. And once you prove it, then those who predict it and those who saw it often win, the Nobel Prize. I thought it was an anecdote, but for me, the space is very. I'm experimentalist and material science and stuff like that. For me, the space is like, wow, that's too big.
It is big and empty and terrifying. I agree.
Yeah.
And actually,
go for it, Alex.
Oh, I was going to say, actually, you touched on something very apropos for today, actually, because yesterday the Particle Physics Prioritization Panel, no, P5, physicists love acronyms. Particle Physics, I forget what the fifth P is, but it was a annual report or it comes out it's not annual, it's every 5 years or so. And a bunch of physicists get together in particle and nuclear physics and decide what are the new interesting things that we want to look for. And I know in astrophysics, you all have a very similar process. I'm blanking on the name.
Astrodecadal.
Decadal, that's right, the decadal survey. And we as physicists and astrophysicists get together, and we really, really try to think about what's the future hold, what are the next interesting things that we can achieve, and what are the things that are just barely out of our reach that maybe with a little more R&D, with a little more study, with a little bit more analysis, can we actually achieve. So if any of you are interested in reading what the physicists think about what we should be looking for in the future and what are the next big exciting things in particle physics and nuclear physics, I'm happy to point you to a very long document known as the P5 report that literally just came out yesterday. And there's going to be many, many public town halls coming up in the next 2 weeks where the entire community is actually invited to give their input on this report and say that and give their feedback on what they think are the priorities. But this has been a very long ongoing process. I've been involved with it for 2 years now, and it's fascinating to watch how physicists make up their minds. Hint, we don't always agree.
That's true. That's so true. And in fact, Alex, I'm glad you bring this up because you asked me which missions I am most excited for, data sets. And in fact, there is one that I am very excited for, but it will show my bias. So as part of Astrodecadal survey, the community made a decision that we shouldn't maybe push for a flagship mission, a single mission that will address one single question or look one particular set of wavelengths, but we pushed for probe class missions with the idea that we're having the budget, but allowing for more solutions to be out on the table. And as part of the probe class mission proposal call earlier in November, I was part of the team that submitted a proposal for an X-ray mission that will get to measure how quickly black holes rotate, and that in turn will tell us something about how they grew. So that is something I'm very excited about, but that's not a mission that's accepted yet. And I'm biased because I am partial to that science case. However, this is genuinely, truly what I am properly excited about, measuring how supermassive black holes rotate with those new space missions.
X-ray astronomy, that's exciting for multiple reasons. I used to work on an X-ray sounding rocket. So yeah, I heard a little bit about the trials and tribulations of trying to get data from an X-ray telescope or satellite. So in the last couple of minutes, I think we're going to be wrapping up now here. I had one last question for you. It's an important one, coming from the field of dark matter. What are your favorite two models of dark matter particles? And there are only two correct answers, namely the ones I've worked on, right?
I have a single favorite. I'm sorry.
Mm-hmm.
And I sure hope I fire out at least one of the two that are yours. So my favorite candidate are axions. And simply because, and it's a very simple and biased justification, because I feel like recently, especially X-ray astronomy has been making great progress in trying to constrain those. And the methods are getting better, and data is only coming, data collection is only coming and becoming increasingly more the signal is becoming increasingly stronger. We are at no point of saying that these are axions, but it would be very neat for dark matter to be first identified by looking at the universe, and then the evidence coming directly from astrophysical observations. So that's a very strong bias. I would love to hear yours.
No, you hit the nail on the head. I just did my postdocs looking for axions here on Earth. And this is what I was saying previously when I was working on some of the world's most sensitive radio antennas, looking for these tiny little depositions of energy that can only come about if an axion transmutes, for lack of a better term, into some photons. And so, yeah, no, axions, I think they're incredible and they're amazing. And they solve a lot of problems in physics, but that's a topic for another day. But yes, no, as a former dark matter hunter, I should say, I'm glad to hear that axions are making the rounds. And fun little factoid about the axion name was that it is actually named after a brand of Italian dish soap, because it was supposedly going to wipe the whiteboard clean of many physics problems out there. So on the topic of Italian dish soaps, I think we're gonna start wrapping up this talk, and I think we're gonna be. I'm gonna hand it over to one of the hosts, who's gonna be able to tell you all about the SAGE program's social media presence.
Thank you so much, Alex. It's always amazing, and I hope you students value the fact that all our speakers don't have a straight path. And if you pay attention, you will find many common things. A mentor, a curiosity, and the mentor might change throughout your career. It might be a teacher when you are in school that makes you stay curious, makes you read something or whatever. And it might be later your PhD advisor, or someone who's not even in your field. Is someone who, we need to find those cheering people that have our back, and that's very meaningful. And you will find that, I think we found it in every single person who's come to talk to us. And you will realize some of you are very stressed out about, I'm in high school, I don't know what I want to do in college. It's okay. We didn't either, right? Isn't it, Asha? It's like a ping ball, right?
Absolutely. We're like photons scattering in a dense medium.
Oh, nerdy.
Sorry. Sorry. But honestly, it's really, really true. And I, as you've alluded to that before, Anna, like I wanted to do art for my undergraduate degree. And then all it took was someone saying, hey, maybe you should try to just believe in yourself. We're doing this. You should do that too. It won't hurt to put in an application.
And science is very creative. That's another thing that often students don't realize, because in school it appears very prescriptive. And but science is very creative. Every day we wake up, we go to look at our data or our experiment. We don't know what's going to be like. Scott, do you know what's going to fail in your experiment? No.
Absolutely not.
No. So every day is a new, is a new surprise. So in that sense, STEM and science and so on is a discovery. Every day is something different. Yes, we read a lot. Yes, we don't know. Sometimes we don't know in which direction what we're gonna find. But we do the same that you guys do in your science project. We have a hypothesis. This, oscilloscope is not working. Is it plugged in? Yes. Do we have the right input signal and so on? So we have lots of fun, and that's the part that keeps us going as well. Anyway, so Danny, would you like to share with our students the information about our social media? We hope that you all stay tuned for the next SAGE Live in February. We hope that you have a great holidays, and to see you again next year. Please let us know if there's a topic that you would like us to address in one of the SAGE Lives. We keep the speakers that we bring represent the information you guys gave us. We know that many of you are watching our sessions on YouTube, and that's great, but we want to see your faces. So we also ask you to follow us on social media at SAGE Camp, and we typically have SAGE Live is on one Saturday a month, and if there is, we know that you guys are very busy because there's soccer, basketball, volleyball, cheerleading, robotics class, but we try to do our best to accommodate with your schedules. So happy holidays, y'all. We hope to see you in February, and if you have ideas for a next SAGE Live, please let us know. Tell Loy what you would like to hear about. We are already planning the sessions for next year. Thank you very much.